Now, let's take a look at some examples. For now, since we haven't yet learned how to do the inverse Laplace, we're going to skip this step, and I'll show you a shortcut that will allow us to find the output for just a couple of signals. For example number 1, we're going to start out with a system that is a mass spring damper system. This is our slinky example that we've been using throughout the class. It's also the process you would use for modeling many other kinds of physical systems, such as suspension systems. We will start out in the same way we've started out before, with a diagram of the system. We're going to label the input and the output signals right away. Here, the input signal is going to be the position of the top, and the output signal is going to be the position of the mass. Next, we apply whatever physical laws apply to this system. In this case, we're going to sum the forces. We say that the balance of forces is equal to the mass times the acceleration. Then we add up all of the forces on this mass. Here we have 2 forces if we ignore gravity. If we are not ignoring gravity, we have 3 forces. We need to make sure that we get the signs correct. If the force is pulling up, the sign should be positive, and if the force is pushing down, the sign should be negative. The spring force will be equal to K times the difference in displacement between X and Y. The damping force will be equal to B, the damping coefficient, times the difference in velocities. In this modeling example, I am going to include gravity because I want to show you how to deal with constants in a Laplace transform. So I'll say that this is minus the force of gravity, m times g. The next thing I want to do is take the Laplace transform of this equation. But before I do that, I'm going to expand this to make it a little bit easier for me to see where the constants are relative to the variables. Okay, now let's take the Laplace transform. Remember that the general rule when we're taking the Laplace transform is that a derivative turns into an s. So m times y double dot becomes the mass times s squared y of s. When we do this, we're assuming that the initial conditions are 0. Now, with the x of t, there is no derivative. So what we have here is simply k times x of s, and the same for the next term. However, this term with damping has a first derivative. So here we do end up with an s. And the same for the next term. Now, what do we do for a constant? Anytime we don't know what to do with a particular value or term when taking the Laplace transform, the first place we're going to look is a table of Laplace transforms. You can find tables of Laplace transforms all over the place. Just open your favorite web browser, go to your favorite search engine, and type in table of Laplace transforms. And I'm showing one here that I found. it covers all kinds of terms that you might potentially see in a system equation. Now what we're looking for is the Laplace transform of a constant, and we see that right here in line 1 of this table. It shows us the Laplace transform of the number 1. Now our constant is not 1. However, we've seen with the other Laplace transforms that anytime we have a constant times a function, we just pull that constant out front and multiply that constant by the Laplace transform of the function. So in our case, we have mg times 1, which equals mg. The Laplace transform of 1 is 1 over s. So that means that the Laplace transform of mass times gravity, which is also a constant, will be mg divided by s. Let's go plug that in. We now have our equation in a form that has the Laplace transform of the input, the Laplace transform of the output, constants, and the new variable s. The next thing we want to do is to put this into the form of a transfer function. Remember that the form of the transfer function is the output divided by the input. So we want to get this equation into the form of the output, y of s, over the input, x of s, is equal to something. Let's do that by rearranging this equation. The first thing I'm going to do is get all of the terms that have y of s on the left and all of the terms that have x of s, that is the input, on the right. Now, can you see from this equation why it is that we typically ignore gravity and simply measure the position of the mass from its equilibrium position? Mathematically, we cannot create a transfer function from this equation. If we would divide both sides of the equation by x of s, we would not end up with simply y of s over x of s on the left-hand side of the equation, because we would still have an x of s term over here in gravity. This makes our math much more difficult. If instead, at the very beginning of the problem, we say that y of t is defined from the equilibrium position of the mass, this makes our math much easier. We no longer have the mg over s term here at all. Because we do not have that term, we can find a transfer function from this equation. The way we do this is first by factoring out y of s and x of s from the left and the right. Next, I'm going to divide both sides by x of s, and I'm going to divide both sides by this term that comes in front of y of s. We now have a transfer function. Let's take a look at another example. For example 2, let's do an RC circuit. Here we will have a battery applying a voltage to a resistor and a capacitor in series. The input is going to be the applied voltage from the battery, and the output is going to be VC, the voltage across the capacitor. Since we already have our diagram, we now need to apply the laws that apply to this situation. Because it's a circuit, the first law we're going to apply is Kirchhoff's voltage law. This says that the applied voltage is equal to the voltage lost in the resistor plus the voltage lost in the capacitor. We know that the equation that applies to a resistor is that the voltage in the resistor is equal to the current through the resistor times the resistance. The voltage across the capacitor is actually my output signal, so I'm not going to write any equation for that. I'm just going to leave it as the voltage across the capacitor. Now, I know I'm not done yet modeling this system because I have a signal, I of t, that is not my input or my output. How could I find an equation for I of t? If I applied Kirchhoff's current law, I know that the current through the resistor must be the same as the current through the capacitor. So what equation do we have that applies to the capacitor? We know that the capacitor equation looks like this. The current through a capacitor is equal to the capacitance times the derivative of the voltage across the capacitor. Since I know that the current through the capacitor must be the same as the current through the resistor, because these things are in series with no other paths around it, I can simply take the current in the capacitor and replace it with the current in the resistor. In other words, I know that the current in the resistor must be equal to the current in the capacitor. I know this from Kirchhoff's current law. So I'm going to plug this equation into this one, and I get that VA of t is equal to C times R times the derivative of the voltage across the capacitor and that's my final equation. I can tell that I'm done because all I have is the input signal, the output signal and their derivatives, and constants. So let's take the Laplace transform. VA of t becomes VA of s. I have no other s's here or constants because there's no derivative being taken of V applied. This next term becomes CRS times VC of s. I have an s here because we've taken the first derivative of VC. Here, there is no derivative being taken, so this simply becomes VC of s. Once again, we're assuming here that all of the initial conditions are equal to 0. The last thing I have to do here is put this into transfer function form. The transfer function form is the output divided by the input. The output here is VC of s. So I'm going to factor VC of s out of this side of the equation. Now I'm going to divide both sides of the equation by v applied, since that's my input, and I want to get the input in the denominator over here. I'm also going to divide both sides of the equation by this term to get it on the other side of the equation. Oops, this is supposed to be a function of s, not of t. Do you notice anything about the difference between this transfer function and the one that we found for the spring? If you remember from the previous unit of class, we know that an RC circuit is a first-order system, while the spring mass damper system is a second-order system. So what is it about the transfer function that clues us in as to whether a system is first or second order? Take a look at this equation, which is a first-order transfer function, and then let's look back at the equation for the spring mass damper. This is the transfer function for a second-order system. What's the important difference between these two equations that tells us the order of the system? The important difference is the power, or the exponent, to which the variable s is taken. Because the highest exponent in the denominator here is a second order, that tells us that the system is second order. You see that the denominator in this equation has s to a maximum power of 1. That clues us in that this system is a first-order system. Let's take a look at a couple more examples. In this final example, I'm going to work through the problem from problem set 2, in which you were trying to model an RC helicopter. However, instead of doing it simply in terms of differential equations, as we did in the problem set, in this example, we're going to do the problem using transfer functions. If you remember this problem from the problem set, we split up the problem into a couple of pieces. The first thing we did is model the helicopter as a mass. And this mass had 3 forces. It had gravity pulling down, it had a damping force pulling down, which was proportional to the vertical velocity of the mass, and it also had a lift force pulling up. Here, the input signal was the lift force, and the output signal was the vertical velocity of the helicopter. We started by summing the forces. The mass times the acceleration is equal to the vertical forces pulling up minus the sum of the forces pulling down. In the problem set, we left it here This time I'm going to go one step further and take the Laplace transform of this equation. I have an s in the first term because we've taken the first derivative of velocity. The lift force will become a function of s. Right away, you may notice that we have here the same problem that we had previously with the spring mass damper system. That is, it would not be possible to get this equation into the form of a transfer function. What we want to do in this case is see if there's some other way we can deal with the term that is troublesome. In this problem, one way I can deal with gravity without having it be its own term is by lumping it in together with the lift force. In other words, if I define the lift force as being the lift force that is in excess of gravity, then I do not need to account for the gravity term. This is similar to the way that in the spring mass damper problem, we defined the zero position of the mass as being the position it would hang at when gravity is pulling on it. In the same way, here I'm going to lump gravity together with the lift force by defining the lift force as the force of lift that is greater than or in excess of gravity. By doing that, my equation is now in a form that can be put into the form of a transfer function. As we move through this problem, you will see why it's advantageous to try and get your equations into a form that can be put into the form of a transfer function. Remember that the form of a transfer function is the output divided by the input. In this case, output is velocity and input is lift force. So I'm going to start by gathering the output together on one side of the equation and the input together on the other side of the equation. We can see that this part of the problem gives us a first order system because s appears in the denominator to a maximum of the first power. Now, in the next part of the problem, we're asked to model the motor. This motor has an applied voltage, a resistance, and motor windings. The input is the applied voltage, and the output is the rotational velocity of the motor. This problem has two physical components to it, an electrical component and a mechanical rotational component. That tells us that the two things we will need to do in this problem are to apply Kirchhoff's voltage law and to sum the moments. Let's start by applying Kirchhoff's voltage law. The applied voltage is equal to the voltage lost in the resistor plus the voltage lost in the motor. The voltage lost in the resistor is current times resistance. And the voltage lost in the motor, we know from the motor laws, is equal to the motor constant times the rotational velocity. Remember that what we're trying to do is get an equation that relates the input to the output. So what we need to replace here is current. I know from the other motor law that the torque of a motor is equal to K times the current. And I know that the current through the motor is the same as the current through the resistor because of Kirchhoff's current law. I'm going to use this equation in here. Next, I need to replace torque. I'll do that by summing the moments. I know that there will be 2 moments on this motor. The torque applied by the windings and the viscous damping, mostly from the blades of the motor spinning through the air. I'm going to solve this equation for torque and plug it in up here. The next thing I want to do is take the Laplace transform of this equation. The reason why I decided to apply the Laplace transform now is because this is the first time when I've gotten this equation into the form of having the input signal, the output signal and its derivatives, and constants. So I'm now going to apply the Laplace transform. I have an s in this term because we have the derivative of omega. I'm also going to change this lowercase omega into an uppercase omega and write it as a function of s. In general, when we take the Laplace transform of a time function, we change the variable to a capital letter. No s in this term because omega is just the 0th derivative. Now I'm going to gather my terms together and write this in the transfer function form, the output divided by the input. To simplify this a little bit, I'm going to multiply the numerator and the denominator both by k. So here I have the transfer function for this part of the equation. We can see that this is also a first-order system, since the highest exponent of s in the denominator is 1. Now, I have an equation that gives omega over VA, And I also have an equation that gives V over FL. My goal is to come up with an equation that has as the output V and has as the input VA. In other words, I want an equation that gives me V of S, the vertical velocity, divided by VA of S, the applied voltage. How could I do that with the equations that I currently have? I could take V of S over FL and I could multiply that by omega of S over VA of S, and I need one more equation. I still need FL of S divided by omega of S. If I had this equation as well, omega would cancel out. FL would cancel out, and it would leave me with my desired relationship, V of S over VA of S. So the last piece that we need is this relationship. In the homework problem, you are given this relationship, that the lift force is equal to some constant times omega. We can take the Laplace transform of this and put this into transfer function form. Now, all I have to do to get my final answer is multiply these three equations together. There's FL over omega, omega over VA, and V of S over FL of S. Let's start by getting V of S over FL of S. Next, let's get omega over VA. Finally, the last piece we need is FL over omega. And this will give us our complete equation, V of S over VA of S.